Hey everybody, welcome back. We're doing section 7 today. Make sure you're putting these notes in your notebook along with your ed puzzle. Don't forget to take notes. Today we're going to be applying the fundamental theorem of algebra. Since we're in algebra 2, this is a pretty big deal for us. Here's one of our key terms, so let's just go ahead and get started. This key term is called multiplicity, which just means another way of saying that there's repeated solutions. So when a function has two or more identical factors, this produces a repeated solution or something we call a multiplicity. So for example, if I factor f of x down to x minus 1, x plus 2, and x minus 1, our solutions would be x equals 1, negative 2, and 1. Do you see how these repeat 1 and 1? That tells me that our solutions of x equals 1 and negative 2, 1 has a multiplicity of 2, meaning it happens twice. Okay, so that's just what it means. Also, if I'm talking too fast or you're trying to write this down and it's going too fast, just hit pause, finish writing it down, and hit unpause, okay? The fundamental theorem of algebra, this is the big thing, says if f of x is a polynomial of a degree, we call it n, whatever the n is, it could be the degree of 2, it could be 5, it could be 100, we don't know. As long as n is bigger than 0 or positive, then the equation that f of x equals 0 has at least one solution, aka root, aka 0, aka x-intercept, in the set of complex numbers. Now remember, a complex number, it could be written as some value of a plus bi. It could be just a regular number, it could be an imaginary number, or it could be a complex number, any of those. Now, the fundamental theorem of algebra corollary, so this is something that goes with it. So FTA stands for fundamental theorem of algebra. The corollary says if f of x has a degree of n, then f of x equals 0 has exactly n solutions. So let's see that play out. So in example 1, it says, how many solutions does the equation x to the third plus 5x squared plus 4x plus 20 equals 0 have? So remember the FTA, the fundamental theorem of algebra corollary, says if the degree is n, it has exactly n solutions. So let's look at the degree here. So we've got these terms, x to the third, 5x squared plus 4x plus 20. We're looking at the biggest exponent. This tells me our degree equals 3. If our degree is 3, that tells me this is how many solutions there are. So however our biggest degree is, that's how many solutions we're looking for. And that's our answer, 3 solutions. So here's our second example. It says find all zeros of a polynomial function. So we're going to be combining what we've learned in section 5, section 6, and now we're combining it into section 7, okay? And the way we're combining that is, number 1, first we're going to look at what's our degree. It's 5, which means we're looking for 5 zeros. Okay, now remember section 6 said, okay, we look at the graph and we're going to use synthetic to get f of x down to a quadratic, which is still the case, okay? So we're looking for 5 zeros, so that means the last section we looked at listing all possible rational zeros, which we learned how to do that. Section 5, we use synthetic to find, to get f of x divided down to a quadratic, and we solve that, okay? So we're going to go ahead and do that right now. So we know we're looking for 5. So here's the thing. If our degree is 5 and we need to get it down to a quadratic, remember a quadratic is a degree of 2. So to get from something from a degree of 5 to 2, we're going to have to use synthetic division 3 times. Because every time you use synthetic, it brings your degree down by 1. So here's what we're going to do. We're going to list our possible rational zeros. That's our step 1. So remember our list, we're going to be looking here at our P, and here's our coefficient here. That's Q. So here we go. P, our factors of P of 14 are 1, 2, 7, and 14. Q is just 1. So our possible list of P over Q, really anything over 1 is just itself. So we know 1 over 1, 2 over 1, 7 over 1, 14 over 1 is just the same list. 1, 2, 7, and 14. Now that we have our list, step 2 is we're going to graph it on our graphing calculator. If you don't have a graphing calculator, you can use desmos.com. But we're going to look at our list here, and then we're going to look at our graph. So I'm going to zoom in. Here's the graph of what you would see. And we're going to kind of give us some starting points. So I see right here, that's one of ours, and it looks like x equals 2. And remember, I said we need to use synthetic 3 times. So we need 3 values of x to start with. Hopefully we can get them. So we found x equals 2. Now look at this right here. That's not our value, x equals -1. Remember how we learned that, that term multiplicity? Here's the thing. A multiplicity happens when it bounces off that value. Do you see how this f of x is like bouncing off of it? It doesn't go through it. We know that this is at least a multiplicity of 2, if not another even number. So when it has a multiplicity of 2 or 4 or 6, it bounces off of the value instead of going through it. So we know x equals -1 at least twice. So we're going to use x equals 2. We're going to use x equals -1. And then we're going to use x equals -1 again in our synthetic division. Okay, so we used our graph to find the values of x that we're going to use. So we used our graph to find values of x to start. And now we're going to use the synthetic that we talked about 3 times. So let's use this first one, x equals 2. So here we go. So we're using synthetic to get our f of x down to a quadratic. Okay, so here we go. 2 goes in the box, and we're going up to our original f of x. I'm going to highlight our coefficients in yellow. We're going descending order, 1, -4, 4, 10, -13, and 14. And that's perfect. There's no missing terms, and we're going in descending order. So we're just putting our coefficients here. And then once we have our coefficients down, we know how to do this. This is easy, right? Synthetic division, pull down the 1, multiply, add down, multiply, add down, multiply, add down, multiply, add down, multiply. And the good news is this remainder is 0, which confirms 2 is a 0. We found the right one. We're not done yet because remember, this is our not down to a quadratic because this is our constant. This is our x squared, x cubed, x to the 4th. We're definitely not anywhere near a quadratic. So we're going to, remember we said we would have to use synthetic 3 times. We're still going to do that. So now I'm going to use my highlighter in green. Remember, we're using this one now, x equals -1, to do quadratic again. We're going to put that in the box. And instead of starting over with these coefficients that we started with, we're going to start with the coefficients that we left off with. Because remember, we just divided that solution of x equals 2 out, and this is our remainder, which is totally fine. It's perfect to keep going and divide without having to start over. Also, this gets us closer to our quadratic, which is what we wanted. So we bring down the 1, multiply, add down, multiply, add down, multiply, add down, multiply, add down. Again, this is a remainder of 0. This x equals -1 is a root. We're good. We're one step closer. We're almost there. And now we're going to use our second x equals -1, which we found here because it had a multiplicity at that root. So we're going to put -1 in the box here. And our coefficients, we're going to use what we had left over right here. 1, -3, 3, and 7. Because again, we want to divide this down to a quadratic. Bring this down 1. We go 1 times -1 is -1, add down, multiply, add down, multiply. And again, that root is 0. That remainder is 0, which means -1 was a root again. And now we can use quadratic formula to solve. So remember, this is 1x squared minus 4x plus 7. So we're going to use that where a equals 1, b equals -4, c equals 7. We're going to say x equals negative b plus or minus square root b squared minus 4ac all over 2a. And we're just going to solve. We do get a negative in that root, which is okay. It's not scary. 16 minus 28, I think we get a -12. Yeah, we get a -12, which is fine. Remember that -12, we're going to pull out the negative as an I because the root of a negative is I. And the root of 12 can really be pulled out as a root 4 times root 3. So that root 4 really is a 2. And then we're going to simplify this again. And we end up with 4 over 2 is 2, plus or minus 2 over 2 is 1, root 3i. So our zeros that we found are 2 plus the root 3i, 2 minus the root 3i. We found -1 and -1 twice. And then we found also 2. So these are the zeros for that one. Good job. So we're all combining all of our ideas from the last 3 sections together. All right, here's our next key concept. It's called the complex conjugate theorem. If f is a polynomial function with real coefficients, which just means real numbers, and a plus bi is an imaginary 0, then a minus bi is also a 0. So friends, here's what all this means. If you see that there's a complex root, you automatically know there's another complex root that it's its perfect match, which is its complex conjugate. So if they give you one, you fill in the blank and find the other. The same thing goes here for irrational conjugates theorem. It says if f of x is a polynomial with rational coefficients, we know that, and a and b are rational numbers, but the root of b is irrational. If a plus b, the root of b is a 0, then a minus the root of b is also a 0. So these kind of go hand in hand in their ideas, where if you see a complex number or a irrational number is one of the roots, it has to have its conjugate, which means its opposite, as another root. So when you see one, you can fill in the blank with the other. So let's just say, for example, if they wanted you to write a function of a least degree, which just means like we're not multiplying any extra things to make it a bigger degree. So it's the most basic function and has a leading coefficient of 1, which again just means we're finding the least complicated, the most basic function we can. And they're saying the zeros are 3 and 2 root 5. We know because of the irrational conjugates theorem that if the 2 plus root 5 is a 0, then also 2 minus root 5 is a 0. So what we're dealing with here is there's really 1, 2, 3 zeros. Okay, remember anytime we have a 0, to put it in factored form, we always go with a factor is always x minus, x minus, x minus. So we know there's 3 roots, so there's 3 factors. And we're going to put every single root straight down into its factor. So we go right here, x minus 3, x minus 2 plus the root of 5. And I'm putting it in parentheses so we don't lose track of a negative, okay? And then we also put 2 minus the root of 5 here. So once we input those solutions into the factors, this is really easy. We're just going to FOIL. The only thing is when you're FOILing anything with the conjugate, do those two first. That's going to make your life easier. So here we go. We're going to go distribute. First of all, we're going to distribute what's inside these parentheses first. We go x minus 2, and then this minus goes to both of these. So minus the root of 5, and this distributes this way here. X minus 2 minus a negative is plus the root of 5. So now we're not FOILing technically because there's 3 terms in each, but it's kind of like the idea of FOILing. We're distributing to every term. So we go x times x is x squared. X times negative 2 is negative 2x. X times the root of 5 is positive root 5x. And then we're going to go the middle terms. So negative 2x, negative 2 times negative 2 is positive 4. Negative 2 times the root of 5 is negative 2 root 5. And then our last one, we're going to go root 5 to every term in here. We get negative root 5x, positive 2 root 5, and negative the root of 25. And I'm losing my room. There we go, 25. So we're just going to simplify what we've got here, which is x squared minus 2x, negative root 5x and positive. So these two will cancel because they're opposites. We have a total of negative minus 4x. So these are gone. And then our last like terms are just our constant terms, our numbers, but negative root 2 root 5 and positive 2 root 5 cancel. This minus root 25 is really a negative 5. So negative 5 and 4 give me a negative 1. Okay, so that's what I have there, but remember, I still need to multiply that with x minus 3. So I'm still going to FOIL that out, and I get x multiplies to all of these parts. So x to the third minus 4x squared minus x. And then I'm going to multiply the negative 3 into those 3 parts as well. Minus 3x squared, positive 12x plus 3. And we're ending up with x to the third, and then negative 4x squared and negative 3x squared is negative 7x squared, minus x and positive 12x is plus 11x, and then plus 3 at the very end. So this is our most basic with the leading coefficient of 1 function for those factors. Okay, last one. Descartes' rule of signs. And actually, I'm going to go over this in class because I feel like this video is too long.